Today I'll be deriving the rotational inertia of a cube. Wait, so let me draw a cube. Where the axis of rotation goes through the middle here. So first thing we need to do is we need to look at this cube from above. And then something you want to notice here is that within this cube there's a cylinder inscribed in it. So we can basically just, we already know the what do you call it? The rotational inertia of the cylinder. Rotational inertia of a cylinder is 1/2 mr squared. So we can we already have a big portion of the cube figured out. So the rotational inertia, but this cylinder right here only accounts for a portion of the total mass, because it's only a part of this entire cube. So we need to find the fraction of mass that it has relative to the whole. And we can just do that by if we to label this R1, and the sides of the square would each be 2R1, right? So we can just do the area of the cylinder over the area of the square, and then that will give us the portion of the mass that this cylinder contains. So it's just pi R1 squared over 2R1 squared, and whoops. And this just equals, well, the R1 squared cancel out, just pi over 4. So that's the portion of the mass that the cylinder contains. So it would be 1/2 times pi 4 m times R1 squared. So that's the rotational inertia of the cylinder that's within the cube. The hard part is trying to find the rotational inertia of the fringes here, the 4 fringes. So let me zoom into each fringe. So let's just take into account this a quarter of this cube here. And then it would be like this. And let's make a new length. Let's say from here, the middle, to a corner, this will be a length of R2. All right? So we know from here to here would be R2. Let's further split this up into eighths. So we're just gonna take an eighth of this cube here. And this is a right angle, this is a right angle. All right, that's good to know. This is a right angle, all right. And it would look something like this. All right, so I just took a half of this, which is an eighth of this entire cube. So let's zoom in on this. So if we zoom in, and it's a good thing to know that this is 45 degrees, because if we take half of what do you call it? Half of this square here, this would be 90, and 90 divided by 2 is 45. So zoomed in, it would look like this. And we know this length to be R1. Now, what I want to do is, let's say I want to find the length of a curve here, like this curve right here. I want to find the length of the curve here. And the length of the curve would be, it would be theta over 2 pi, if we're in radian mode, times 2 pi r. That would be the length of the curve. Its degree equivalent is theta times 360 times 2 pi r. But if we're in radian mode, it would be this. So the length of the curve would just be theta r. So let's say, if we look here, let's say the curve is here. That means we can draw this to be r, and let's say this is r. Let's call this angle alpha, and let's call this angle theta. All right? So the length of the curve here would be this theta here times r. That's the length of the curve. Remember, we're only looking at 1/8 of this total cube here. So we need to multiply by 8 after we're done here. So we need to find this angle theta. We know what alpha is though, because cos alpha is adjacent over hypotenuse r. And this we know to be 90 degrees because we took it from here. All right. So cos alpha is r1 over r. Alpha equals inverse cosine of r1 over r. And we know theta plus alpha is 45 degrees. So theta plus alpha is 45. And since we're in radian mode, let's turn it to pi over 4. So we know that theta equals pi over 4 minus alpha, and alpha equals negative cos, or cos negative 1 r1 r. And if we multiply r to both sides, we get the 1/8 of the length of the curve. So theta r equals r pi over 4 minus cos negative 1 r1 over r. And let's multiply 8, because we only took an 1/8. So we split this up into 8. So we're only considering this part right here, but we want to consider 1, 2, 3, 4, 5, 6, 7, 8. So that's why we're going to multiply 8 to both sides. So that's the length of a curve with respect to r. So I'm going to write this on a new page. So 8r pi over 4 minus inverse cosine of r1 over r. All right. And now, if we look back at this square here, or the cube here, we can make this curve here into a rectangle. So we can spread it out into something like this. And we have to sum these rectangular prisms together. So this length here would be dr. The height would be, well, since the height, it will just be 2r1, because each side length of the cube, as we said before, is 2r1. And this length here would be the length of the curve. It would be this. So we already know what the volume is. It would be this times dr times 2r1. But this only gives us the volume. We want to find the sum of mr squared. So we need to add a volume times density is mass. So we need to find density. The density is the total mass over 2r1 cubed, because 2r1 cubed is the volume. So we just tag on density here, and we finally need to add r squared here. And then we take this integral from r1 to r2. Why from r1 to r2? Because if we look here, this is r1, and this is r2. We already taken into account the cylinder, but we need to take into account these fringes here. So that's why we're doing it from, well, r1 to r2. All right, I hope that made sense. Now, if we look at here, let's take out the constants first. So we know rho is constant, or density is a constant. We notice 16 here, or 8 times 2 is a constant, and we notice r1 is constant. So we just get, and let's combine this r squared here with this r. We get r cubed pi over 4 minus cos 1r over dr. All right, and let's further split this up. So let's not let's just forget about this here, and let's just first split up this integral, because I'll run out of space if I, include it. So we know this integral just simplifies down to this, and we already know what the integral of this is. This is the tough part. So we're gonna further ignore this part and only consider this part for the moment. All right. Oh, times r cubed. Whoops. We need to tag on r cubed here, because it distributes to there. Okay, so now we're trying to find the integral of this. Okay, and we're going to use integration by parts. So u dv and lipet. So we're going to make this du, and du would equal, well, I'll find du later. V is here, and dv would be r cubed times dr, and this would be r4 to the 4. Now, to find what du is, so cos u would equal r1 over r, derivative negative sine u times u prime, equals r1 r squared. Du equals r1 r squared sine u. Cos squared plus sine squared equal 1. Hence, sine u would equal 1 minus r1 squared over r squared. And then this would just equal, right. Yeah, this is right. Okay, and then du would equal r1 r squared 1 minus r1 squared over r squared. Okay, now we multiply u and v, so we get that r4 over 4 cos negative 1 r1 r minus the integral of, let me think, yeah, r4, 4, wait, yeah, I think this, and r1 r squared 1 minus 1 squared r squared. All right. Now this is an easy, or this is already integrated. Now we just want to find the integration of this. So we're going to do another uv. So this just simplifies down to, these r squareds cancel out, right? So this is just simplifies down to r1 r squared over 4 times 1 minus r1 squared over r squared, I think. And let's multiply r to top and bottom. So we get this. r1 r cubed over 4 r squared minus r1 squared. So I multiplied r to top and bottom. If I multiply r to the bottom, this would become r squared, and this r squared just cancel out. So yeah. And we're gonna make u this time equal, let me think. Let's make u equal r1 r squared over 4. And hence du would equal 2 r1 r, or whoops, over 4 times dr. And then dv would equal the remainder, which would be r over, look, I only took r squared here. There's still an r left. So we get this. And this way we need u substitution for this. And if we do u sub, I'm just going to do it really quickly in my head here. Yeah, this just becomes r squared minus r1 squared, I think. Because if you take a derivative of this just goes to the bottom, and then chain rule 2r on top. Wait, let me think. Yeah, if you take a derivative of this, there will be a 1/2 associated with this root sign, and the 1/2 will cancel out with the 2 from the chain rule, and this and becomes r. So yeah, this is the integral of that. And then we do this, r1 r squared over 4 r squared minus r1 squared minus the integral of, well, this. Well, that just cancels out to 1/2, but we'll deal with that later. And we know the integral of this, so let me just rip out this page. So the integral of this right here, well, we just do, let me just write it out and make this into a 1/2. The integral of that will just be, let me think. Well, all right, I'll just give you a u substitution. And then du would equal 2r dr. dr would equal 2u over 2r. So root u r1 over 2 times r, and we exchange dr times du over 2r. So we just get the r's cancel out, r1 over 4 du. Hence, we integrate this, we get that this becomes 1.5. r1 u to 1.5. This becomes 1.5 times 4 is 6. And yeah, that's the integration of that. and this would equal, well, u equals that. Over 6. All right, now we have everything ready. Okay, so the first thing we derived was this. This would be the rotational inertia of this cylinder inscribed there. So let's just multiply 2 with 4, we get 8. So pi 8 m r1 squared. Pi 8 m r1 squared. All right. The second thing we found was this. This, we already know what the integral of this is. The integral of that would just be, let me see, this would become r4, pi 4 from r1 to r2. Oh, before we get into anything, let's look at this. So we need to find a relation between r1 and r2. R1, and R2 is this diagonal here, right? Then you can easily see that R2 equals root R1 according to Pythagorean's theorem. All right, so R2 equal root 2 R1. So this is equals root 2 R1. Oh yeah, and we need to remember what this is. Oh, so this is where the math becomes really ugly. And let me think for a while. So let me first solve what this is. This constant here, which is that. So it would be this times 16 times R1. So this just simplifies down to, well, 2 cubed is 8, right? So it just end up being 2m over R1 squared, because this R1 cancels that with that R1 cubed on the bottom. All right, so it would be this 2m R1 squared. All right, so the integral from this would be pi 4, well, root 2 times R1 to the 4th power would just be 4 R1 to the 4th minus R1 to the 4th, and hence this is just 3 R1 to the 4th, so 3 pi 4th R1 to the 4th. And then we look here, when we multiply, hold on, let me think. Yeah, that should be right? Wait, hold on, I think I made a mistake somewhere. Oh, whoops. I forgot when you integrate that, this R4, yeah, should be a 4 here. So this would just be 16. All right. So when you integrate, the exponent becomes a 4 and the denominator becomes a 4. So this becomes 16, and yeah, this should become 16. So we get that this constant right here multiplied by 2m r1 squared, and this becomes an 8. So what we get is something really nice, which is 3 pi over 8 times m. This r1 squared cancels out with that, m r1 squared. All right, and then you can see a pattern here that this is simplifies down to, or this is the rotational inertia of the cylinder, and this is the rotational inertia of whatever we calculated here. This becomes pi over 2 m r1 squared. All right, now we've got this part done. Now we need to look at that part. All right, so the first thing we calculated was, so this is a negative symbol, right? So first UV we calculated was this. And we also need to write this constant, which you found to be 2m r1 squared. So 2m r1 squared. So minus, what's the first UV? Let me think. The first UV was, yeah, where was the first UV that we calculated? So, oh yeah, never mind. It would be here. This thing right here, that's the first UV we calculated. The second UV we calculated was this thing right here. So minus R1 R squared over 4. Yeah, I'm almost running out of space here. And then the last one would be the integral of this. And we just add a plus sign. Because this negative distributes to here, so negative, and then this becomes a plus. And the integral of that we found to be right here. Plus R1 R squared minus R1 squared to 1.5. And this would be integrated from R1 to root 2 R1. All right. So let's begin integrating. First thing you want to notice here is that for this, cos inverse cosine of this, of 1, just equals 0. So if we plug in R1 here, we just get 0, but cos which equals pi over 4. All right, so for this thing right here, we just get, let me write it out. For that term, or this term right here, we just get, well, if we plug in R1, we get 0. So we only need to care about this limit. And if we plug in here, we just get 4 R1. The 4's cancel out, so I'll just write it down for you. 4 R1 to the 4th over 4 times, well, this just becomes pi over 4. All right, now let's look at the second term. When we plug in, oh, let me focus. Yeah, when we plug in R1 into here, this just becomes 0, but when we plug in root 2 R1, we get that root 2 R1, let me see, if we plug in root 2 R1, we get R1 times 2 R1 squared, I think, over 4. Root 2 R1 squared would just be 2 R1 squared, and then this just becomes R1 squared. And finally for this, we get that, well, if we plug in R1, it would become 0. So root 2 R1 here, like, oh, this just simplifies down to R1 squared, because root 2 R1 squared is 2 R1 squared, minus R1 squared is just R1 squared. R1 squared to the 1.5. That's 1.5, by the way, all right? And now let's just simplify this. And that's the easy part. Pi over 2 m R1 squared minus, well, 16, 8. So this will have, well, no, these 4's cancel out. This would have a coefficient of a half. So pi m, this cancels out with that. So pi R1 squared over 2, because 2 and 4 cancel out. Yeah, this cancels out with that. There's, okay, I shouldn't have canceled out here, but this was originally a 4. So R1 to the 4 over R1 to the squared just gets us back to this, multiplied by m. So pi m, let me see if I got that correct. Yeah, the 4's cancel out, okay. And then we have this, which is just, becomes R1, so we get R1 cubed. No, R1 4 over 2, the 2's canceled out, yeah, m negative plus R1 squared. I think that's what happens, right? R1 4 over 2, R1 squared, yeah. And then this becomes negative, because negative positive is a negative. This is R1 3, R1 4 over 6, R1 4 over 3, R1 squared, m R1 squared over 3. All right, and first thing you notice is this cancel out. This becomes 0. And then we just get, these can also combine to get 2m R1 squared over 3. And finally, we found the rotational inertia of a cube. that's the rotational inertia of a cube that goes through a point here. And you're going to see this formula more commonly with S, where S equal 2r1, or where S equals the length of a side, which is 2r1. So let's write this in terms of S. So that means r1 equal S over 2. We plug in S over 2 here, we get 2m S over 2 squared over 3. One of the 2's cancel out, so we just get ms squared over 6. All right. That's my method of finding the rotational inertia of a cube. And I'm pretty sure there's a shorter way to do it, but I couldn't find a shorter way. So yeah, that's all. I'll give you the steps to the proof. So we started from here, then we went from here, then we finally went to here, then we finally went to here. All right. See you in the next video.